Hello my friends, let's see the following exercise for today. We have this following function with two branches, and the question is there a solution of g of x equals to 4 minus square root of x in the interval between 1 and 2 open? To understand how to solve this exercise, we first need to understand clearly what is being asked. First, note that I'm not asking you to find a solution for this thing. What I'm asking you is there a solution for this thing? So that's the first part. The second part, what does it mean, is there a solution for this thing? G of x equals to 4 minus square root of x? Well, first, this part here is a definition of a function. And the function, well, let me define the function for you. So g, the function g, will map all the real numbers, because the domain of this thing is all real numbers. It will map reals into reals. And every x, which belongs to the real numbers, is going to be mapped into the number g of x. And g of x is just an abbreviation for either this number, when x is less than 1, or g of x is an abbreviation for this number when x is larger than 1. So this thing is a definition of a function. Now, in other words, it is an assignment. I want to reinforce this idea. What's here is a definition of an assignment of x and g of x. On the other hand, when I ask, well, a solution for this thing, this is not a definition of a function. What's here is an equation. And why is it an equation? Well, because again, g of x is an abbreviation for a number. So g of x is an abbreviation, for example, for x cubed plus x, because this thing is true for x larger than 1, so it's true for this interval. And so essentially g of x is an abbreviation for this. So when you substitute this thing here, well, you just have an equation for x. And is there such a solution for that equation? Well, this is what we are seeking to answer. Now, let's first see it intuitively how to solve this thing. For that, let's make the following picture. If you have a function, so this is first the interval between 1 and 2. We have some function, it doesn't matter which one, for example, like this. Notice from this picture alone the conclusions that we can just take. Well, if the function is continuous, which it is, and if the image of 1 is negative and the image of 2 under this function is positive, I think it's obvious to you that this function must cross the horizontal axis somewhere between 1 and 2. So this is f of x. But to say that f of x crosses the horizontal axis somewhere between this thing is the same thing as saying that f of x equals to 0 as a solution between 1 and 2. On the other hand, if our function instead behaves like this, again, the image of 1 is positive, the image of 2 is negative, so they are different. The function is continuous, and so it must cross the horizontal axis somewhere. But at the cross point here, let's call it C, for example. Well, C is a solution of this equation. So if you substitute, grab this C, put it here, the left-hand side is going to be, you compute the left-hand side is going to be equal to the right-hand side. From this picture alone, you can get ideas for what we have to do to answer this question. So, there are several things that we have to make sure. First, is g of x continuous? We have to check that. But before going into that, let's try to adapt what's written here to what's written here. Because here we are asking for a solution of this equation, while on the picture we are we have a strategy to seek for solutions of a function equals to 0. So let's adapt to this thing. And for that, let me just recast this equation like this. G of x minus 4 plus square root of x is equal to 0. And now let me define this number here as being f of x. So f of x is an abbreviation for this number. This reformulation essentially just puts our question in this form, because to ask is there a 0 for f of x? Is there a 0 f of x for f of x in this interval? Is the same thing as saying does f of x equal 0 as a solution in this interval, which in turn means does g of x equals to 4 minus square root of x as a solution. So you have these different problems, they are all equivalent. But the version of the problem that says g of f of x is equal to 0 is exactly what we need to use this strategy here. So we just reformulate the question so that it's good enough, is in the right form for us to use this strategy. So let's use it. The strategy essentially involves, well, first check whether the function is continuous, and then check whether the images at the beginning of the interval and at the end of the interval, well, do they have different signs? So let's see it. Well, first, is f of x continuous in this interval? So this is the first step. First step, is it continuous? Well, from 1 to 2, let's see. Let me just write. Is f continuous in the closed interval, not the open one? You will soon see why on the closed interval. Is it continuous in this interval? Well, let's see. This thing here is true for this interval. So from 1 up to 2, it's clearly continuous. Why? Because in this interval, g of x is this part, because this part is true for x larger than 1, okay? So this is, g of x is like this, in this interval, well, but this is just a polynomial. And any polynomial is continuous in its entire domain, which in this case is R. Well, if it's continuous for every real, then it's continuous in this interval. Okay? So, indeed, g of x is continuous on this interval, but is it continuous on this interval? So we have to check that. We have to check whether this function g of x is continuous on the closed one. So we have to check for continuity at 1. So let's do it. So to say that g of x is continuous at 1 means that the limit of this thing, of g of x, when it approaches 1 from the left, is equal to the limit when x approaches 1 from the right, which is in turn equals to g of 1, the 1 itself. So we have 3 things to compute. They are quite easy. So let's do it. Let's do it here. So the first one, the first limit. I think we can do it here. For example, it's 4. So this is the limit x minus 1 of 4 plus 2 divided by x minus 2, x minus 2. Well, you just substitute, right? You just substitute, what do we get? Well, you have 4 here, plus 2 divided by 1 minus 2, but 1 minus 2 is minus 1. So you get 4 minus 2, which is equal to 2, right? Now let's see the second one. The limit when x goes to 1, using the plus, so you have to use the second branch, because we are after 1, here. So you have x cubed, here, let me see if you can see it, plus x. You just substitute, it's 1 plus 1. So it's this thing is equal to 2. And what is g of 1? Well, we use the first branch, right? But I think you can immediately see that's again 2. So these two limits are 2. This is 2. And also the image of 1 is 2. So because all these equalities are true, well, the function is indeed continuous at 1. The function is continuous at 1. Well, again, conclusion. G of x is continuous at 1. Well, it's continuous after 1, so it must be continuous in this interval. So it is done. The first part of our strategy is done. The function is indeed continuous on the interval of interest. Now, the second part that we want to check is the images at the endpoints. Well, g of 1 is already computed, so it's 2. So f of 1, let me just do it one step at a time. F of 1 is equal to g of 1 minus 4 plus square root of 1. Well, this is 2. So it's 2 minus 4 is minus 2. Minus 2 plus 1, so it's minus 1. And at the other endpoint, we have to compute f of 2, which is g of 2 minus 4 plus square root of 2. But what is g of 2? Well, let's see. We use what branch? The first or the second? Well, 2 is larger than 1, so we use the second. So we have 2 cubed, which is 8, plus 2 is 10. 10 minus 4 is what? 6. 6 plus square root of 2. Of course, only the sign matters for this case. So this is positive, and this is negative. So again, we have a situation, you are in a situation like this. This is 1, this is 2. At 1, the image of f is below, here, and at 2, it's above. So we have just computed here these 2 points. Moreover, we know that it's continuous. So if I have to draw the f function, well, and connect, it has to connect this point and to this point, because they both belong to f. But to do that, I have to cross the thing here. You have to cross somewhere between 1 and 2. But it is, if it crosses the horizontal axis in this interval, that statement is the same thing as saying that f of x is equal to 0 as a solution in that interval. But that means that this thing has a solution in that interval. But in turn, that means that this thing has a solution in that interval. So we have just confirmed the thing. So the exercise is essentially solved. Now, before so this exercise is solved, but first let's look at let's go one step further with this and see the logic of the problem. I want you to see the logic of the problem. So let's state, because what is at end here is what's called the Bolzano intermediate value theorem. So let me just state the theorem and see what the theorem has to do with what we have just computed. So the theorem is like this. So the Bolzano theorem. Let's call it Bolzano theorem. What does it say? Well, it's an implication. It says the following: if the function is continuous, so if f, in mathematics, how do we say that? Well, to say that a function is continuous is the same thing as saying that f belongs to the class of continuous functions, the C class of continuous functions between a and b. So C is a set of all functions that are continuous in this closed interval. So by saying that f belongs to that club, well, f is continuous in that interval. So this is the first part of the Bolzano theorem, to say that f belongs here. The second part is to say that the image of f at the endpoints is different. And how do we write this thing in mathematical terms? Well, it's just multiply the endpoints. So to say that f of a and f of b have different signs is the same thing as saying that the product is always negative. I think it's obvious because you say at one endpoint is negative and at the other is positive, then the product is negative. If at this endpoint is positive and then at the other it's negative, well, the product is negative again. So this is a statement that encapsulates both situations. So these are the sufficient conditions for the Bolzano theorem. So what's the conclusion? If this thing is verified, then in conclusion, what we get? Well, we say that there exists some number C belonging to the open AB. So there is a C in this interval that guarantees that f of C is equal to 0. So this is essentially the statement of Bolzano. And this is essentially what we have just seen in this exercise, in this lecture in the beginning, intuitively on the graph. Now, in the logical terms, this is exactly what we have. Now, let's use this tool. Let's use this tool. To use it, well, first we have to check that the function belongs to C between A and B. In A and B, in this case, by the way, it's 1 and 2. So this is 1 and 2 here. So you have to check it. Well, we just did here. We just check it that the function is continuous in this interval. Because, first of all, it's a polynomial. And moreover, G is continuous at 1. So our G is indeed continuous. In turn, F is continuous. Remember, F is continuous because G is continuous and the square root is continuous. Moreover, you just verify this thing here. So you computed f of 1 and f of 2. Well, this is negative, this is positive, so the product is negative. So our definition of f fulfills the sufficient conditions. So as a consequence, there exists a C between 1 and 2 that guarantees that f of C is equal to 0. But saying that is the same thing as saying that there exists a C that makes this thing true. Now, one final remark regarding this thing. Why is it important for us to have continuity at 1? Why couldn't it be just between on the other points, continuous at the other points? You have to specifically verify that at a point, at this endpoint, the thing is continuous, like we just did here. Why is it important? Now, notice this. If the function, for example, was not continuous at 1, if the function was not continuous, it would be possible for the function to behave like this. So, open, and now it jumps like this. Can you see? So, we would be computing this thing and checking that the signs are different. They are indeed different, the signs. But the function is not continuous, well, exactly at this point 1. It just jumps. And so this thing does not cross the horizontal axis. So it's very important that a function must belong to C between A and B closed. Can you see? To exactly prevent situations like this. Okay? So you have to check everywhere. It must be continuous at every point, including at A and B. Of course, B we need not to verify because this is a polynomial and polynomials are continuous, well, in its entire domain, and so it must be continuous at 2, for example, in this situation. So we must verify this thing, okay? Now, and that's it.